Okay, everyone, so I'm actually not going to complete this one because it's pretty much identical to the ones we've just been doing. So calculating solution concentration is where you have information about one substance, but you're missing the concentration of the other, right? So for example, here, the equivalence is reached when we have this volume of potassium hydroxide and we have the concentration, and then we are adding it to, and we have the volume of acetic acid, and we're looking for the concentration. So literally it's the same setup. You write out the balanced chemical equation, and actually this one is a 1-to-1 ratio. So if you want to give this a try, the concentration for the acetic acid, so should end up being 0.0, and it should be 3 sig figs, 603. Okay, so if you give this a try, like I said, there's no tricks or anything in here. You're looking for concentration. You find moles, mole ratio, boom, then you find your concentration. Now, these next two are a little bit different because it shows you actually some sample data that you would get from a real titration equation. So here we have lactic acid, which is found in sour milk and yogurt and cottage cheese, and it has the flavor of sourdough, which there's a COVID way back playback, sourdough bread. So we have 3 different trials. So each trial used 25 mils of lactic acid. So the concentration of the NaOH, so let's actually write out the balanced chemical equation. So our lactic acid plus our NaOH ends up making water, and we have sodium with our lactate. Okay, so the concentration of NaOH we have 0.153 moles per liter. We have the volume here for the lactic acid, 0.25 liters, and we want the concentration of our lactic acid. And the volume here, so this is where it's different. So here you have the 3 trials. They're not just telling you how much volume it took to neutralize. They did this 3 different times. Okay, so when you do a titration, it's always recommended that you do it in triplicate. But when you're actually calculating this, you actually will remove 1 out of the 3 that kind of looks like it's off from the other 2. Now, these are all pretty close to each other, but if you notice, you have 0.42, 0.61, 0.59. So this first one is further off. Like if you take the difference between each of them, this one is really a very small difference compared to 0.61 to 0.42 or 0.59 to 0.42. So you always remove 1 out of the 3 that's off. Okay, so the volume that we would use here would be the average of those 2. So it would be 33.61 plus 33.59 and then divided by 2. So the volume that we would use for this particular reaction, and let me put this in liters, would be the average of the 2. So anytime you're dealing with actual trials, right, you would do the same procedure. You would take 1 out, and then now at this point, it would be exactly the same as what we've been doing. You would find the moles of your NaOH. In this case, it's actually a 1-to-1 ratio. So then you would get the moles here and then solve for concentration. So really the only part that's new to this compared to the other, the other examples we've been doing this whole time is the fact that you are now taking an average from an actual data chart. Okay, so this, the final concentration, so if we were to work this out, so you would do C times V here. So you would get moles of 5.132 times 10 to the negative 3 moles, which would then be, of course, it's a 1-to-1 ratio, so it's the same. So the concentration for our lactic acid would be our mole value, 132 times 10 to the negative 3 moles over our volume in liters. So we end up getting here, and then we want, so all of these would be, you look at this for significance as well. But because we have the concentrations 3, which is lower, we would report this to 3. So 0.205 moles per liter. Oh my gosh, my M there. Okay. This third one is literally identical to the one we just did. So you have a methylamine compound, and we have some pesticide, which is used in pesticides and a solvent, blah, blah, blah. Okay, so we have here a 0.185 mole per liter hydrochloric acid, and we have samples of our aqueous methylamine. And so these are all our HCl, because remember, your burette is always the standard, the one that we know the concentration of. So in this case, I guess what's different from between here and here they told you the total volume that was used. Here they give you the final and initial. So actually, I guess this is giving us, in fact, another step. So to figure out the total difference, you do your final minus the initial, right? So for this first one, I'm just going to write it beside it over here, just because I kind of wrote all over that. So you would do 47.65 minus 20.14, which would be a volume of 27.51 mils, right? 36.88 minus 9.55, so this is 27.33 mils. 43.11 minus 15.84 is 27.27 mils. So you would do the same thing here. You would get rid of the trial that has the that's most off from the others. So in this case, we would get rid of that and take an average of those two. All right, so you would set this up the same way. You find your moles, you take an average of this to use for your volume, and then you end up having, it's a 1-to-1 ratio again in this particular case. So your concentration here for your methylamine should be, again, this is going to be 3 sig fig, 0.101 moles per liter. Okay, so let's look at a different type of problem. So all of those, everything we have been doing up to this point has been calculating an unknown concentration. So, all right, sorry about that. I had to pause the video. Okay, so we have now the situation. So remember, we're looking at each of those scenarios. So this is where now we would be calculating the solution volume. So to be honest, it's not all that different from what we've been doing. The only difference is now we're finding the volume instead of the concentration. So let's take a look. So we're looking for the volume of, we have a KOH solution reacting with H2SO4. So remember, when you're writing these reactions out, you are writing out the neutralization process. So this is different than when you're writing equilibrium Ka expressions, right? Like you're not moving over one proton. So you're just completely neutralizing these, right? That's the purpose of titration. We want to have the equivalence moles of acids and bases. So here we would need 2 and then a 2. Okay, so we're looking for the volume of KOH, and we have the concentration. And we're told that we are neutralizing. We have a volume of 0.015 liters of sulfuric acid and a concentration of 0.173 moles per liter. Okay, so you will always have two pieces of information for one compound or one component, and you're missing something of the other one. So here you would still have to find moles, right? So we would do our 0.173 moles per liter times 0.015 liters, which will get us 2.595 times 10 to the negative 3 moles. Okay, now in this case it is a 2-to-1 ratio, so we would have 1 H2SO4 for every 2 KOH. So for our moles of KOH, we would have to then do times 2, which would be 5.19 times 10 to the negative 3 moles. Okay, so once you have your moles of KOH and you have your concentration of KOH, volume is simply going to be, right, so you're doing your C is equal to N over V. Volume is going to be N over C. Right, so it's going to be 5.19 times 10 to the negative 3 moles divided by our concentration, moles per liter. So for this one, we would need, and also for when you're finding volume, just an FYI, I know it asks specifically for milliliters. If it doesn't specify what unit to do your volume in, it doesn't matter to me if you do milliliters or liters, obviously as long as if your sig figs are correct. So we need 3 here. So this is going to be 24.1 milliliters, right, once we convert that over. Okay, so very, very similar. Literally, instead of using C is equal to N over V, we're using V is equal to N over C. So you would have always 2 pieces of information for one, and you're missing for the other. So let's take a look at this. So a little bit of a twist. Obviously, they tried to show you different scenarios. So the next 2 we are going to work out because they're a little bit different. So a solution of HCl is standardized to have a pH of blah, blah, blah. Okay, so what they're allowing us to do by telling us this is we can find out the concentration that way. What volume of this solution must be added to 25 mils of a 0.285 strontium hydroxide to find equivalence point? Okay, so we have HCl plus strontium hydroxide, which is going to make our water, and strontium chloride. And then we're going to need a 2 and a 2. Okay, so we have here, we have the concentration of this, 0.285 moles per liter. We have the volume of our strontium hydroxide, and we want to know the volume here, and we can find the concentration. So how we're going to find the concentration is if we do, just a kind of a little side calculation here. So if we do 10 to the negative pH, remember that's going to give us our concentration of hydronium, or which in other words is the same thing as saying hydrogen ions. So 10 to the negative 0.432, which is 10 to the exponent negative 0.432, which is 0.3698. Let's just do just 0.37. Okay, moles per liter. Now remember, because this is a strong acid, all of that HCl is becoming hydrogen ions, so really this is the concentration, right, because it's a 1-to-1 ratio. So this is 0.37 moles per liter. So a little bit of what we did in chapter 5 there, coming back to haunt you maybe. Okay, so we have a concentration. So again, now at this point, so that was the little twist on it. Instead of them straight up telling you the concentration of HCl, you had to use the pH information to get the concentration of HCl. At this point, it's literally the same now as the other one. So you would find your N, you would then, right, so doing C times V, you would then look at the mole ratio, right, it's 2 to 1, so you'd have to double it. Then once you have your moles, you would solve for volume in that way. Okay, so I'll kind of just preview obviously what's different about this, but when it's something like this where the rest of it is the same, you should be able to access it at this point. So 3, the volume you should get here is 38.5 milliliters. Okay, so number 3, again, a little bit of a different twist on things. So here we have a 5.6 liter sample of a gas at STP. Right, so just a reminder, STP means that you're going to have 22.4 liters for every mole of that substance. And we have it's dissolved in enough water to make a 500 ml solution. A 20 ml sample of this solution is then titrated with this concentration. What volume of the standard solution, which is this. Remember, the standard solution is what you know the concentration of, is required to reach equivalence point. Okay, so let's write out our reaction here. And actually, I'm going to pause this so we can get to the next part on this.